To resolve the zigzag behavior, we can utilize Hessian matrix. So suppose that the domain of f, your loss function f, is open and f is twice differentiable. Then we can compute Hessian matrix at every your parameter space. Okay? And Hessian matrix, this is very important matrix in your optimization process. Basically, Hessian matrix represent the local curvature shape. Okay, so once you know every Hessian matrix at every your point, then you can understand every curvature structure of your loss surface. Okay, so this is very nice. So for instance, Newton's method update your parameter in this way. You compute xt plus 1 is equal to xt, the previous time slot your parameter vector, minus step size gamma times inverse of your Hessian matrix multiplied with your gradient vector. So here you do not use the vanilla gradient vector, simple gradient vector. Instead, you multiply the inverse Hessian matrix so that you can go to the local optimal point more directly. Okay, so when you multiply this inverse Hessian matrix, this kind of contour of your loss surface becomes, after you multiply inverse Hessian matrix, your loss function becomes very regularized. So your gradient direction becomes more directly go to the local optimal point. So Newton's method converges faster to local minima point compared to the vanilla gradient method. The inverse Hessian matrix controls the step size adaptively, so that considers the local curvature structure of your surface. But the problem of Newton's method and the problem of all the second order methods, so this type of method using Hessian matrix is called second order optimization method. All the second order optimization method has a very significant problem, very crucial problem, the computational complexity and memory requirement. So Hessian matrix and matrix size or matrix shape proportional to the number of parameters. You have to store every parameter pairs, partial derivatives multiplied at the partial derivatives. So if you have millions of parameters, then you have to store millions by millions partial second order partial derivatives that representing your Hessian matrix. So that is very huge, and even worse, you have to compute the inverse. You have to compute the inverse Hessian matrix for the Newton's method. And basically the computational complexity to obtain the inverse matrix is very huge. When you have n by n matrix, so it is known that the computational complexity to obtain the inverse matrix is roughly n cube operations you need to obtain the inverse matrix. So if you have millions of parameters, you have 10 to the 6 number of parameters, basically the required number of operations roughly 10 to the 18. So this is very, very huge, and this is not allowed in practice. So we have to introduce some heuristics or some alternative way that do not use the Hessian matrix, but roughly guess the inverse Hessian matrix or some other technique that can boost up your convergence speed. Okay. The first approach is momentum method type. So momentum methods, the idea of momentum method is this. So when you look at the zigzag behavior, at every time slot you have completely opposite direction. When you have a very steep curvature, so when you have this type of low surface, because we have very high gradient to this direction, you have very huge, very active movement to this direction. But since the curvature to this direction is very slow and very small amount of update you can observe to this direction. So when you're averaging the trajectory, so when you add up the past trajectory history, you can expect that to this very steep direction, because you can observe this very opposite directions update, zigzag behavior. Basically it can be cancelled out. So you can slow down the movement for this direction when you add up all the trajectory, the past history of your trajectory. On the other hand, to this direction, very slowly varying direction, very smooth directions, the averaging of your past history, there's no cancel down, it just adds up, because all the past history share the same direction. So from the momentum method, what you can expect is you can slow down the movement toward the very steep direction, and you can boost up the movement toward the very slowly varying direction. Okay, so you can expect this momentum type of method can speed up the convergence to the local optima. And as we discussed earlier, Nestrov accelerated gradient descent and momentum method are very similar. They are pretty much the same, except this point. So momentum method compute the gradient with the previous time slot parameter vector, but the Nestrov accelerated gradient method first move with your past history and then compute the gradient. So that is only one difference between momentum and Nestrov accelerated gradient method. So the philosophy of them basically the same. Using the averaging, we can slow down the movement toward the very steep direction, and we can speed up or boost up the movement toward the very slowly varying direction. Okay. And another good property of momentum method is because momentum method is averaging the past history using this type of moving averaging. So how to compute the averaging? So basically this momentum method multiply the eta to the previous history. So it sequentially store the m value sequentially store the past history by moving averaging, and then add new information. Okay, so the ratio eta and gamma actually control how much your new information contribute to the m vector. If eta is close to 1 and the gamma is very small, then the momentum method will keep a lot of past information. On the other hand, if this eta value is very small and gamma is big, then basically this momentum method remove most of past history and very depend on just at the moment gradient. So the current gradient is the most important thing. The past history is kind of meaningless. At the case, you have to set eta is very close to 0 and gamma is high. So you basically control the past history and current gradient vector using eta and gamma parameter. Okay, and this kind of averaging also works very well with stochastic gradient descent algorithm, because stochastic gradient descent algorithm GT is a random vector and of which expectation is equal to the gradient of your true loss function value. And this noise, what is noise? GT minus expectation of GT. Because this is a zero mean random vector, when you add up multiple random vector having zero mean, the average, the expectation of the sum of random variable having zero mean always equal to 0. But the variance will decrease as you add more random variable. For instance, if you compute 1/3 times x1 plus x2 plus x3, the variance of this random vector will be smaller than the variance of each x1, variance of x2, variance of x3. If all x1, x2, x3 share the same variance. Okay? So averaging basically is very nice approach to reduce the variance of random sum. Okay. So that's why momentum type of method works very well with deep learning applications. At that time, we usually use stochastic gradient descent using mini-batch. So the stochastic noise can be cancelled out using the momentum method, so which can increase speed up your conversion speed, and also because we can reduce the noise, the trajectory more accurately convert to the local optima, so you can expect better performance. Okay. And also in deep learning, you have a huge number of parameters, and when you have huge number of parameters, your alpha and beta is not balanced. So you have very tiny alpha, you have very high beta value. At this time, you probably have zigzag behavior, and momentum method can resolve the zigzag behavior, as I explained earlier. The second approach is the square of gradients based approach. So there are two algorithms, ADA-grad and RMSProp, and both algorithms compute the G vector, and G vector is basically averaging of gradient square. So here the gradient square is element-wise square. So every time you compute the gradient vector fxt, so it has all the partial derivative values with respect to each parameter, and gt vector basically just compute the gradient of each element, square of each element, and then adding cumulative the square of gradient vector every time. Okay, ADA-grad just add up, and RMSProp is moving average. multiply eta to the past history and multiply 1 minus eta to the current gradient scale. And then using this summed g vector, you normalize. Okay, using square root of gt plus epsilon, you normalize your gradient vector. Again, this is element-wise computation, so you have a gradient vector, and each element of your gradient will be normalized by square root of gt, the corresponding element of gt plus epsilon. So why the gt is useful? Basically, the square, one nice thing of square is you don't need to consider the sign of the value, right? So from the square, you can roughly guess the absolute value of your gradient vector of each element. So sum up all your square element and then take a root, then basically you can roughly guess the absolute length of your each gradient vector element. Okay, and again, let's consider this kind of contour of your loss function value. To this direction, your g vector having very high value because your zigzag trajectory will have very high partial derivative to this direction, but very low partial derivative to this direction. Okay, so when you compute the gt vector, this direction will have very high value, but this direction will have very small value. So when you normalize your gradient by square root of gt, you can expect very the high denominator value to this direction, but very small denominator value to this direction. Okay, and which can make your trajectory like this. Okay, and you can expect much faster convergence. Right. But the key difference between RMSprop and ADA-grad is this. In RMSprop, we basically take moving average. But ADA-grad, we do not averaging the scalar gradient vector. We just add up. Add up. Then the scale of gt value roughly is proportional to the number of iteration t. So this gt value has one side effect, time dependent learning rate gamma. So this term roughly becomes proportional to 1 over square root t. And 1 over square root t learning rate is very nice learning rate. We actually discussed the 1 over square root t learning rate in our midterm exam.